Hi everyone, my name is Herta Montoya. I'm a PhD student in the Lyle School of Civil Engineering at Purdue University. I will be talking about resilience from an engineering perspective. The title of my presentation is Designing for Resilience. Let's start by answering the question, what is resilience? The most used definition of resilience is the ability of a system to adapt, withstand, respond to, and recover quickly from any kind of adversity, so that people are safe. We live in a complex world where we have communities that have different types of infrastructure. It can be physical, like roads and buildings, or systematic, like the health and education system. But our communities as a whole face adversities more often than we think so. We have earthquakes, wildfires, tornadoes, hurricanes, pandemics that affect our communities. We expect communities to have a level of performance that is acceptable or optimal, what we can define as a healthy state. But whenever we have a natural hazard or pandemic or any kind of adversity that hits our community, we enter into a damaged state, one that we must recover from. The ability to go from a damaged to a recovered state, how we bounce back, that is the process of resilience. Community and system resilience have very different components. Here you can see some of the general categories that are part of a community. As engineers, we mostly help our communities in the area of physical infrastructure, and it is why I named my presentation Designing for Resilience. And to do that, we need to design, keeping in mind that we will face inevitable events during the healthy state before an encounter with a threat. We need to adapt our systems or infrastructure to the needed requirements and make preparations in advance so that we can enable recovery in the future. Once a threat hits, our already designed for adversity systems are able to withstand the blow by returning partial or full functionality. And those 3 steps will allow the system to recover from a threat in a timely manner. All this is needed so that we can minimize the drop in our performance, and this is known as a resilience-driven design approach. What are the general steps for a resilience-driven approach? First, we need to identify the hazards. By knowing what are the conditions that cause injury or death to people, damage or loss of equipment, or that can harm the environment. We assess these hazards by defining the risks. And risk is the combination of how frequent an adverse event occurs and what are its consequences. In that way, we can select performance objectives and design for those, so that in the resilient context, we have minimal loss of functionality. And finally, through simulation and other tools, we can evaluate the performance of the systems to see if they really meet our initial objectives. Let's look at an example through the eyes of a structural engineer with seismic building design. Many cities in the world are exposed to high seismicity, meaning that they have frequent and sometimes strong earthquakes. In these cities, during an earthquake, there are buildings that have structural members, such as beams and columns, that sway from side to side. And just like we get tired whenever we move a lot or exercise, the buildings also experience fatigue when moving from side to side. And sadly, this leads to fatal consequences, such as collapse and loss of life. So that we do not face that, is that structural engineers, along with researchers and some governmental agencies, have developed a performance-based design for these buildings. We can design buildings that reliably achieve target performance objectives. Opposite to other approaches, in which people look for the response of individual elements in the building, like columns or beams, the performance-based design looks at the building as an entire system. If an earthquake hits, this building by design will remain operational and safe. Remember that it all starts by identifying and defining hazards. We identified that earthquakes are a risk, and that the frequency of occurrence is tied and increases with how severe the earthquake is. So we define earthquakes as frequent, occasional, rare, and very rare. Now, what are the outcomes that the buildings may turn out to within an earthquake? They may remain fully operational, or just operational, meaning that they can provide some services, but not all. Life safe, as people are not at risk, and near collapse. Having those two components, I can build a matrix of performance where I can define basic objectives for my design. I want the building to remain fully operational during a frequent event and to be near collapse with the very rare and strong one. Anything beyond that is not acceptable. But not all buildings are equal. So I need to define essential and safety critical objectives, because a home or gas station is not as essential as a hospital, or school, or supermarket when we hit an adversity. So I need more rigorous objectives for highly important infrastructure. Now, what if I tell you that we can take this resilience-driven design, safety-driven approach out of this world, like the moon or Mars? And I mean this literally. Resilient extraterrestrial habitats. Here at Purdue University, in partnership with UConn, UTSA, and Harvard, form part of the Resilient Extraterrestrial Habitat, RETH for short, Institute, funded by the National Aeronautics and Space Agency, to develop the technologies needed to establish habitats that can adapt, withstand, and recover from adversities in outer space. And this is a project that has engineers and scientists from very different backgrounds, all to solve a complex problem that has to do with resilience. The RETH team has broken down the resilience-driven design into three main tasks. First, to design by anticipating and adapting to possible threats. Secondly, to develop sensor systems, part of a habitat that can actively learn, detect, and diagnose if there are any issues in their performance that may affect the system as a whole. And third, but not least, to develop robot technology that is able to help and operate independently to maintain the performance required and also collaborate when humans are present. When it comes to extraterrestrial design, some of the existing approaches are driven by entirely avoiding or minimizing the occurrence of known anticipated faults, but in reality, that is an inadequate approach for the design of long-term space habitat systems, because disruptions or adversities are inevitable and difficult to predict. Therefore, we need to design to face these adversities and withstand them. If we take what we've learned from Earth to see a system as complex and with tightly coupled elements, we can mitigate the cascading failures due to one single problem. We need to anticipate and adapt to possible threats. In a space habitat, what are the possible threats that we may encounter? We can have meteorite impact, which can harm or damage the habitat as it hits at very high velocities. And just like in Earth, habitats on the moon can experience moonquakes, most of the time cascading events from meteorite impact. Another threat is temperature fluctuation. We can reach very high temperatures when the sun is irradiating in the habitat's direction, and very low temperatures when we're at the dark side of the moon. Dust storms are also a threat, as they can damage equipment such as power generators that surround the habitat. Keeping in mind all these threats, we can design a habitat and define unsafe regions and a safe region of performance over time. One can define a desired trajectory, but in reality, the system will behave something like this, because it will face adversities that may push the system towards the unsafe region. We want to develop smart habitats that can respond to changes, damage, and anything that could go wrong, and still maintain its integrity and safety. Sometimes we will deviate from the desired performance. The systems within the resilient habitat will catch this deviation and will raise an alert to take action. And there is where a preventive measure comes into play. You designed and planned ahead of time that your system will catch irregularities and maybe adapt to the threat and come back to the desired performance. What happens when you get a little bit too close to the unsafe region? You will then need an interventive action. You respond to the threat. You might call on the robots for help, or your system will deploy other resources and bounce back to a safer point. And maybe your system will not be the same, but you planned ahead of time to have mitigative actions that adapt to the new normal and restore the ideal functionalities. To achieve such a behavior is that the team is working in developing sensor technology that can actively learn how the system works, detect or catch irregularities, and diagnose the sources of the issues. Whenever you need intervention, robots can come to help, sometimes along with humans if present, and already have a set of solutions for the different things that could go wrong because you planned ahead of time. As future engineers, scientists, or maybe public officials, it doesn't matter if you designed for resilience in Earth or for the Moon or Mars, but what matters is that you design for systems that can adapt, withstand, respond to, and recover quickly from any kind of adversity. We live in a complex world where we can contribute by designing resilient systems that will benefit a higher purpose. The earlier we start seeing the world through a resilience mindset, by addressing our potential threats in design, the safer our systems can be. Thank you for your attention, and I hope you enjoyed this presentation.